Hi everybody, I just wanted to do a run through of the answers to the check for understanding, so I'm just going to take it now. This is a preview. My answers won't be shown to students. Okay, so the questions are randomly ordered, so this might not be the same ordering as yours. Here it says restructure this equation by isolating. Okay, so let me drag over. Why can't I drag my thing? Okay, so here we are. So here I've got cube root x minus 3 minus 1 equals x. So I want to isolate the cube root, so I'll add 1 to both sides. So x plus 1. Now I'll cube it. So cubing both sides gives me this. Let's go ahead and cube this. So I know this is the same thing as x plus 1 times this squared, which is going to be x squared plus 2x plus 1. And now I'll expand this one. So I'll get, let's see, x cubed plus 2x squared plus x. And then here I've got another x squared and another 2x and a 1. And so I can add all those up. And I've got x cubed plus 3x squared plus 3x plus 1. And then on the left-hand side, it's always the same here. So I've got this. So now to put it in standard form, I'm going to move everything to one side. So I'll add 3. So that gives me 4 here, because I got the 1 and I got the negative 3. And then I'll subtract x from both sides. So that gives me x cubed plus 3x squared. But then I subtract an x here and subtract an x here. So that gives me 2x. Okay, so I think I've got my answer here. So it's going to be x. Oh, I've never used the student interface. Nope. Oh, I see. Okay, so x cubed plus 3x squared plus 2x plus 4. Is that right? Yeah, great. All right. It says write the equation for f of x, which should be a transformation of this that has a vertical asymptote at blah and a horizontal asymptote at blah. Okay. So I just want to sketch what I want so I can think about it better. So vertical asymptote at 3 and horizontal asymptote at negative 1. Oops. And then what was that last condition? Oh, negative 3. Okay. And then that last condition says f of 0 is less than negative 1. So here's f of 0, and here's negative 1. So if f of 0 is less than negative 1, then I've got a point down there, which should mean that my curve looks like this. And something that I'm noticing is that's actually flipped from like the regular 1 over x function, which looks like this. So I think I've got to do a couple of transformations. Oops, normal 1 over x function looks like this. So I'll take my normal 1 over x function, I'll shift it left by 3 by doing that. I'll shift it down by 1, but then I also want to vertically reflect it, so I'll put a negative sign there. And you can double check that all of that stuff works. Like if I plug in 0, clearly I still have a vertical asymptote. Sorry, if I plug in negative 3, I still have an asymptote in the right place. If you imagine the end behavior as x gets really, really large, this whole term approaches 0 because the denominator is approaching something large, so I still have an asymptote at negative 1. But now if you plug in 0, what do I have? I've got negative 1/3 minus 1, and so that's definitely less than 1. In most people's answers who got this almost right, you didn't pay attention to that f of 0 is less than negative 1 condition. You just kind of ignored it entirely. All right, so the answer is, negative 1 divided by x plus 3 minus 1. Notice my use of parentheses here. If I left the parentheses out, this is actually saying the opposite of 1 over x, and then the plus 3 is on the outside. I didn't take off points for this, but you should just know that you're not typing it right. All right. What's next? So isolate and undo. So this is a two-step isolate and undo, similar to what we did in class. Let me write down the problem and then we'll do it. So here we've got root 1 minus x minus root x equals 2. So first I want to move one of these to the other side so I can then square both sides. So I'm going to move that one. So that's 2 plus root x. Now I'm going to square both sides. So on the left, squaring the root undoes the root. On the right-hand side, let's expand it. So I've got 4 plus 2 root x plus another 2 root x is 4 root x plus root x times itself just gives me x. But I'm not done yet because I still have this square root x here. So what I need to do is I need to move everything else to the other side so that way I can square one more time. So I'm going to subtract x from both sides. So that gives me negative 2x. I'm going to subtract 4 from both sides. So that gives me negative 3. Now I've got 4 root x here. Now I'm in a good position to square both sides again. So on the right-hand side, I've got 16 times x because I squared the 4 and I squared the root x. On the left-hand side, I'm going to expand this. So negative 3 times negative 3 is 9. Negative 3 times negative 2 is positive 6x. And now I've got another positive 6x. So that gives me positive 12x. Negative 2x squared gives me positive 4x squared. Sorry, negative 2x times negative 2x gives me positive 4x squared. And then I still got a 16x. Okay, so now let's move everything to the same side. So I'll subtract 16x from both sides. And that gives me 4x squared. If I subtract 16 from 12, that's negative 4x. And then I've still got the plus 9. So that should be the answer. So here I've got 4x squared minus 4x plus 9 equals 0. All right. Let f be a 25th degree polynomial and g be a 23rd degree polynomial. What degree is that thing? All right, so let's think about that. So my question implies that the answer doesn't depend on what kind of 25th degree polynomial. It implies that if I've got 5x to the 25th plus a lot of other stuff, it's going to be the same as if I just have this. So I'm going to figure this out just by using a small example. So here's a 25th degree polynomial. Here's a 23rd degree polynomial. Okay, so now it wants to know what is f of x squared minus 2 times g of x. Okay, so let's just substitute. So if I substitute that in for f, I've got 5 times x squared to the 25th power minus 2 times 3x to the 23rd. Okay, so when I simplify this, this becomes x to the 50th because of the exponent simplification rules. This is now 6 times x to the 23rd. And the degree of this equation is clearly 50 because 50 is the highest power of x in the entire polynomial. And hopefully you can see that it doesn't matter what else I write here. If I had other terms in these equations, I would still get the same answer because the degree only depends on the highest term, the highest power term. So it doesn't matter what the lower power terms are. You could calculate them out, but they're just going to create more lower power terms in the final answer. And those lower power terms in the final answer don't affect the degree of the final answer. So I think as far as a method goes, the takeaway here is I asked a general question, but you can answer it for yourself by using a specific example to think. So here it says factor the expression blah. You would factor out first. Okay, so I'm seeing common factors in each term, but it looks like only x squared because the coefficients 5, -6, and 1 don't have any factors in common other than 1, but like that doesn't really make sense to factor out. Yikes, what's happening? Oh, x squared? Nope. X squared. Yay. Okay, that was weird. Okay, last one. Okay, so why does this thing have a horizontal asymptote and that thing doesn't? So this was more of an A-level kind of a problem. What you have to do is you have to go back to what we said in class about what produces horizontal asymptotes. So in class we said that if you've got k is a real number, so k is just any constant, divided by any function x that's increasing, then limit as x approaches infinity equals 0. And the reason why is because if g is an increasing function, then that means when x is getting bigger, g of x is getting bigger. And if g of x is getting bigger, that means the overall expression is getting smaller, approaching 0. So let's take a look at our specific case here. We've got 1 over x plus sine x. Okay, so what does this look like? If it was just 1 over x, it would look like this. However, I'm adding sine x, and you know that sine x is going like this. It's like oscillating up and down. And I'm adding the red height to the black height here. So this function, if you were going to kind of sketch it, should look something like this. It's going to have x, but then you're either adding a number whose biggest value could be 1, or you're subtracting a number whose biggest value could be 1. Because this is just oscillating between 1 and -1. So you know that as x is getting bigger, you're still going to have that oscillation, but your overall function is still going to be increasing because of the plus x. So a really nice answer to this would have been saying something like, as x goes to infinity, x plus sine x is also approaching infinity, which means 1 over that function approaches 0. What about the other one? Why does the other one not approach? So here I've got 1 over x sine x. So in this case, we're multiplying. So one sort of easy observation is the sine function looks like this. If you're multiplying by x, that's sort of like scaling it. So you're just stretching it. You're stretching it by different amounts depending on the x value, but that doesn't matter. You're still going to have an infinite number. So the denominator here, this part only, y equals x sine x, this is still going to have an infinite number of x-intercepts, namely at all of the, let's draw the unit circle here. So sine x is telling me the y value. So you're still going to have intercepts at integer multiples of pi. And it doesn't matter how big you get. So because you're always crossing the x-axis, that means that the denominator isn't just strictly getting bigger, it's still oscillating as x increases. And so if the denominator is oscillating, it can't possibly be the case that the overall fraction is approaching 0. Because the overall fraction is also going to be oscillating between positive and negative values. All right, that was it. I hope this was helpful.